After the countdown. So that looks all right. Huh?
Tam je mikrofon. To pomeni, da je furt. Ne, ni bil so dobro, ne, štiri tako. Ne, pa je bilo rdeče. Ja. Še tako pomeni.
No, yeah? Great. Good. Now just go pee. I'll be right back. I'm sorry, say that. Okay. Okay. Yeah, that's so fun. Follow along, ask questions. I don't know. Hey. Thanks. Hi.
People just need especially the first half of the session.
Absolutely. Yeah. Any. So we'll give her 2 more minutes. So I guess we're on the button. So it was a good point. So first of all, there's many other exciting talks going on. So if you feel you want to go to any of those, or this is not the event for you, then don't feel bad about leaving, okay? You should only be here if it has interesting stuff for you. So teaching functional programming, I hope this session is going to evolve in some sort of interactive conversation or something, but I'll make some opening remarks to kind of set the mood for it. Maybe I'll go back a little bit. My name is Mike Sperber. I'm CEO of a software consultancy in Germany that works using functional programming. We also have sort of the leading German language blog, I think the only German language blog on functional programming. And we do commercial projects involving just about any functional language that you might name. If you're anywhere near Berlin next March, then we also run a really nice developer conference. And that also doesn't exclusively focus, but mostly focuses also on functional programming, but really has folks coming in doing practical development with them. So today, though, I want to talk with you about teaching. So just to give you a little bit of background, so my first official class I gave teaching programming was in 1987, 88, when I was an exchange student in the US, and I gave an AP computer science class at Radford. Who was alive then here in this room? Okay, well, so there you go. So I subsequently worked for the University of Tübingen. I think, what I have to offer today anyway is an effort that really started in 1999 when we offered an optional course for humanities majors might have been 1997, I'm sorry, it started here. And then we developed a class on introductory programming for the University of Tübingen that is still in use today, essentially, of course, a more developed and continuously improved version of that. And of course, now I'm in the commercial space, and we've been doing commercial training on functional programming for about 10 years now. Specifically, we offer also introductory classes on functional programming, but we also offer training on what's called functional software architecture. And if that is something that's interesting to you, sort of functional programming in the large, then there's going to be an open space here on Thursday where which is kind of a disparate field. So I'd love for you to be there. We need a couple of people to show up. No preparation needed. So, and of course, you can imagine, having lived a long life teaching, that kind of everybody around me has suffered from me trying to teach them something. As you can imagine. So I kind of want to open the conversation by giving you something to think about, right? I'm sure every one of you has a functional programming language that they really think is really cool, that they like maybe best out of all of them. It might be OCaml, it might be Haskell, it might be, whatever. It might be Erlang, it might be Scheme. So everybody's got their favorite language. And somehow, and this is not exclusive to functional languages, this always evolves into something because it is my favorite language, right? It also has to be the right language for teaching, right? And that's a fallacy. So if there's one point I want to make today, is that just because something is your favorite thing and because you found it compelling or you find it compelling, right, does not mean that it is the right thing to use for teaching, because ultimately, I'll have a slide on that. Your students are not you, okay? And they're probably not even you a couple of years ago. I guess this slide is kind of getting old. Does anybody here in this room know what this book is? Okay, very few people. So this was a book that originally was published in the 1980s. I got to say 1980s, a long time ago. And it's a book about the introductory course at MIT. And you would see a lambda right there. So even then, almost 40 years ago, they were doing this using functional programming. And they were doing this using a functional language called Scheme, which has, which is immediately compelling because it's a very small language. It has an extremely uniform syntax, so you don't really need to spend a lot of time teaching the syntax and the elements of the language, and you can instead focus on the concepts of programming. And it's a book I highly recommend it even today. So it's one of the great books of computer science because it has beautiful worked through examples of using abstraction and many concepts in programming today. And looking at it, you immediately think, I think most people think this is a wonderful thing to use in my class, right? It's got this really nice syntax. It's a small language. Scheme can be used to explain the features of just about any other programming language. So you can use it to, and they do use it to explain also imperative programming and object-oriented programming. We could go any level of detail. So you might think that knowing Scheme, you could transition easily into any other language just by sort of explaining it in terms of Scheme. And this was not just compelling. I remember reading that book also at the end of the 80s. And I've also found it immediately compelling, as did a lot of other universities, specifically in the US and all over the world, because they saw this book and they thought, oh, this is compelling to me. It's also the MIT's position on how to teach the introductory course. And a lot of universities then tried it and failed. Right? And so strangely enough, right? And lots of culprits, people are looking for culprits. So some of them said, well, this is because, our students are not as smart as the MIT students and whatnot. So all kinds of explanations were found. A lot of the computer science department used it to have an argument over the programming language, said clearly because it's not C++ based or Java based, that's going to be the culprit. But the consensus was that this works at MIT, and it just for various reasons, other schools are different, doesn't work there. But actually if anybody can find one of the original TAs from MIT, they'd find out that it never worked at MIT either, right? And MIT has since at least revised their curriculum. I suspect still not to a very productive place, but that's on a different page, and we can talk about that. So these questions, whether it's got small syntax, whether it's a uniform language or something like that, these are all compelling questions, but these are the wrong questions to ask when you're thinking about teaching the introductory class. So, but sure enough, if you look again, if you can see, this is the best copy I could find of this paper, right? Also from the 80s, Phil Wadler. I don't know if he's going to be here, but usually here at ICFP. So Phil Wadler said in the early 90s, then said, well, so Adelson Sussman is this book I just showed you, has said clearly the problem is the programming language is if you just switch to Haskell. This is the 1990 version of Haskell, so it doesn't have impredicative types and so on. So if you just switch to Haskell, then everything will be better. And he said, well, this is because Haskell has a different set of language features. It has pattern matching. Its syntax isn't as uniform, but it's close to traditional mathematical notation. A static type discipline. Of course, static types are great if you are a Haskell programmer, and it's got lazy evaluation, which is also great if you're a Haskell programmer. But notice that the word student does not occur on this page, right? So I'm not going to say that it's something that can't be made to work, but it's very difficult. At the end of the day, Haskell is not a very good language to use in an introductory course, but neither is Scheme, despite the fact that it's much more uniform and smaller than Haskell is. It's something that we learned the hard way. So really, if you're teaching at the university level, for the longest time, starting in the late 90s, I had this experience. I would teach, right? And because I love, the Lambda calculus and functional programming, I was really into Scheme. I try to impart that excitement about, the techniques and technologies that we were using on our students. And this is something that you can make work in just about any context, because students will walk up to you and tell you that they were indeed motivated and excited by your excitement and passion. The Lambda calculus is the most wonderful. So some students will come up, right? And it took me, many years to realize they all kind of look like that one, right? So some students come up to you and they make you feel that you're doing the right thing, that your teaching is being successful, but those people are not the problem. I realized after a while, it doesn't really matter what I teach, right? There's always going to be students coming up to me telling me that they like what I'm teaching, but the problem is there's also a bunch of students who are not coming up to me, okay? And those are really easy to miss. So they're not Eugenia Cheng, they're not Simon Peyton-Jones. They don't have that crazy look on their faces, whatever. So there's various differences between us and our students. I mean, one of them is obviously that we're further along in our learning process, right? And so here's a great book I recommend. It's called Why Students Like School. and it's got these catchy chapter titles. And here's one of them, which says, well, cognition, I mean, your brain literally works differently when thinking about programming than that of your students. So you can't, by kind of looking at your own brain working and you're looking at your own understanding of the concepts of programming, you can't infer from that those same processes will just magically, sort of diffuse over to your students in a classroom setting. Okay, is that clear enough? Right? So that requires different kind of approach. Moreover, here's another trap you can fall into. Who's familiar? Who knows what Seymour Papert was? Also at MIT, coincidentally, also involved with the logo programming. Well, no, okay. We're all the people, everybody who was actually born when I started teaching. Anyway, so who's heard of one laptop per child, though? Okay, so a couple of people have heard from that. So this was a project, one laptop per child, was a project founded by Seymour Papert, who was a professor at MIT, who invented a programming language also based on similar ideas, I think, as Scheme was, but definitely as part of the same group, and subsequently founded this one laptop per child project. And the idea was this, right? You remember, it was this really cute laptop that you could power by just turning a crank. And the fundamental idea was this: if you just make material and tools available to kids and students, they will just learn by themselves. Okay, they will just teach themselves essentially. So that was an idea called constructionism. So that's what you see here in that chapter. So and Papert really hated a traditional, really disliked the traditional classroom setting, and said, well, the way to do that is not to kind of teach. The way to teach people is not to telling them stuff and talking to them and something like that. It's just making tools and techniques and material available to them, and then they would just learn. Now, you might have heard that the one laptop per child project failed, right? And one of the failures was the failure of that idea. I think one of the places where you can read about that was there's a paper by Alan Kay on the history of Smalltalk, who the Smalltalk group, right, was working on in the late 70s and early 80s on what is now object-oriented programming. And they heard of the early ideas of Logo. And Logo really was something that was designed to be accessible to children. And of course, again, they fell into the same trap as I mentioned in the beginning. They thought, we're working on Smalltalk. Smalltalk is our favorite programming language. Ergo, it must be the right programming language to use for teaching. So we'll just try to use the same kinds of ideas that Seymour Papert had developed at MIT, and we'll just try doing that with Smalltalk instead, because Smalltalk clearly is a more favored and superior language than Logo was. Now, but to their credit, they actually looked at the results. And if you look at the paper, it says, oh, it was really gratifying. Students came up to us and said, this is the most wonderful thing we've ever seen. But then they realized that, after a while, they realized that all those children that were excited about Smalltalk really were from very well-to-do schools, or from a very affluent neighborhood around Stanford University. And if they looked at the broader population, they said that whatever they were teaching, which was completely natural to them, the Smalltalk designers, was not at all obvious to the students. Okay. So this thing, it's compelling to you, does not necessarily mean it's compelling to your students. So, and if you're more interested in kind of what the failures were for the One Laptop per Child project, then there's a paper, but also a book by Morgan Ames, which goes into excruciating depth about what went wrong there. And so in particular, I don't know if that's what you're interested in, but while I was at the university, one of our goals was to really teach a broad student population, right? And so if your goal is just to kind of select your top, 5%, work with those, then I don't have anything to say to you. Then, whatever you do is probably going to work. Just do your favorite thing. But if you really want to reach a diverse and broad, cross-section of the population, then this is not the thing to do, right? Ironically, the laptops that they wanted to drop over Africa, over severely underprivileged children, only work for highly privileged children, right? So there's some sad irony in that. Okay, so so that's, I mean, I could essentially stop there, but let me go over some of the sort of outcomes of that and kind of what we did to deal with this idea. So again, from Daniel Willingham's book, so one of the failures in thinking, I think, from the old PC project was, again, remember, it's about if we just supply the tools and the material, then students will learn naturally. And one of the things that work against you is that thinking is hard work, right? It's not something that everybody does naturally because they like to do it. If you like to do it, you are not normal, right? So just got to be clear on that, right? But still, a lot of those kids and students can learn how to program, right? It's not just the hard thinking part about it is not something that they naturally enjoy. And so, one of the successors, for example, from the logo and One Laptop Per Child project is something called Scratch, which is a block-based programming language. Again, really, really compelling. There's, in fact, an even more functional version called Snap, which has more of the concept of scheme and has continuations even, and things like that in the language, but it's still block-based. Those are great. Those are wonderful, compelling tools. I invite you to try them out. But I talked to their designers, and even, in Germany at least, this is being used to teach at the high school level quite a bit. These tools were not made for teaching programming to kids. These were tools programmed for digital storytelling. This is also fun stuff. It is not the same thing. Okay, so and you get very similar results. On the other hand, there's also positive things to be said, right? Is that if you work on something hard enough, if you manage to get over that hump that thinking is hard work, then your what we call intelligence is something that can be changed and improved through hard work. And that's something I think that a lot of people in education have understood over the years. And so they thought, well, we just have to, provide some kind of object or something, some scenario that will then compel students to invest a lot of work, a lot of practice, and then, then their intelligence will be changed and they'll learn how to program. And particularly, this almost always if you've looked at educational initiatives, those usually involve robots. I don't know if you've seen that. Particularly, this is also something that happened at MIT, right? So you can find students that are excited about robots. They will program those robots, and they will then, so the theory goes, they will then learn how to program because they are excited about robots. But I think, again, this falls into two traps. So the first one is, I've looked into some of these educational initiatives, right? And they also tend to favor privileged kids who have a lot of spare time, right? This is a privilege when you're a student, right? To have a lot of spare time to put into things. And moreover, here's another quote from William's book, memory is the residue of thought. So if you think about robots, you're going to think about programming is incidental to the building of robots, right? So you'll think, my conjecture here is you'll mostly think about robots. So those are sort of fundamental traps, I think, that you can fall into when you're teaching. So, and here's another one. So a lot of programming books, and that includes books about functional programming, right, are based on something that I call learning by example, right? So I just tend to present this because it's to disarm object-oriented languages, but you can find the same for functional languages, right? Is that, there's lots of books. Specifically in the Java space, there's lots of books that say, well, you can learn programming in 24 hours, 72 hours, something like that. And the way that they work is, well, we will introduce new features in the programming language, and here's one or two examples for those. And now go forth and program your own program, right? So here it says, we're gonna, that chapter says we're going to make a guessing game app, and then it says, well, we're going to because it makes sense to use a while loop in that game app. Here's a while loop. Here's an example, right? And then you go present your own problems for the students to solve. And in my experience, this is something that works very poorly. So a lot of students just don't transition from seeing a bunch of examples to actually writing their own programs. And even if they do, those programs look like this often, right? Because there's no systematic construction principle. There's just, here's a couple of features in the programming language, and here, how you assemble them into a working problem, into a working program is something that's left to you, okay? Does that make sense so far? So common mistakes are, well, students are like us. What I love must be great for teaching. Students will figure it out themselves. That excitement about something, this is also a political issue in my experience, right? A lot of politicians will talk about educational initiatives in the terms, we must get kids excited about STEM subjects or something. You'll hear that a lot. At least you hear it a lot in Germany, which is, and they don't understand that excitement does not translate into competency at all, like ever. So my experience doesn't translate at all, right? Something else is required. And specifically, if you kind of base your educational approach on excitement, you don't get an equitable, if that's what you're interested in, you don't get an equitable experience, because you get students who can afford to be excited and put their time into what they're excited about, rather than, what maybe we as a society need, okay? So, and all of these fallacies apply equally to sort of traditional, whatever, object-oriented classes as they do to functional programming, yeah? Even though we might think that our programming concepts are more compelling than the object-oriented, whatever other concepts that you might know about. And they're right. You're right to some extent, but it's not enough to create a good educational experience. And so if you live long enough and you teach long enough, you have the luxury of kind of doing something like this, right? You kill your darlings, poster in my office. You get the luxury of just of observing that certain things that you're doing in your teaching don't work, and just dropping them and replacing them by something else. And my experience has been the things that end up working are rarely the ones that were compelling to you from the outset, okay? So, let me be clear on the goals that I have. Your goals might differ, right? So my personal goals usually when teaching, doesn't matter if it's in an introductory class or if I teach professional programmers, right? I want them to be able to build well-constructed programs to put their imagination into something, to put whatever requirements, business requirements, or just something from their imagination, to translate that into a well-constructed building or whatever it is, piece of software, right? So it's not digital storytelling, it's not experimental science, it's not data science or something like that, right? Those have their own educational challenges. I'm just not qualified to talk about them, okay? So one of the things that I learned the hard way, even though I shouldn't have, was because, I mentioned at the beginning, I was an exchange student in the US in the 1980s, and here's my English teacher. And she gave out a handout at the beginning of the class that looked, well, I'm going to zoom in here. And said, well, during this class, we're going to be writing a bunch of compositions. You are going to be writing, the students, we're going to be writing a bunch of compositions, right? Every couple of weeks, you would write a composition, a paper. And she would say, well, if you're writing a composition, here's a structure, right? You can see there's kind of an outline here. And if you zoom in, you can see, okay, so some section of your comp is going to be a body. Usually it's 3 paragraphs. And the first paragraph usually has those 5 elements. And it would go on. So essentially what this outline would do, it would tell you your comp is going to be, it has so many sentences. The function of the first sentence is this, the function of the second sentence is. So it's a very rigid structure, right? And coming from Germany to the US, I was instantly going like, I don't need this crap structure. I know how to write a composition, right? I don't know if you've dealt with, the same attitude I sometimes would get from computer science students who'd had, classes in high school or something like that. They would go to the university and I've written programs before, right? I don't need rigid structure. So I was like an instant rebel in that class. And it took me a while until I realized this is really, really effective at just getting off the ground, right? If in order to write a comp, I would just go along that outline, I would kind of fill out the form, and I would have a reasonably structured comp at the end, right? And you do this a couple of times, you realize, what the reasons are the structure being the way it is, and you could slowly transition to sort of more degrees of freedom as you write compositions. So this is something that I knew in '87, but that I kind of forgot, right, in teaching, where I thought, whatever, I don't know how you grade students, right, but we always, in German university, you grade students on the correctness of their answers, certainly not on the adherence to some fixed structure, something like that. So, I mean, one thing that you might object to that's very fashionable, I mean, maybe should have had that slide earlier, is it's very fashionable, also specifically in the constructionistic approach, is to claim that the disadvantage of the traditional classroom is that students are very different. They're very differently paced. They have different mental structures to deal with things and so on. And therefore, the classroom where somebody's in front and just tells you something, right, doesn't work. But cognitive science doesn't really support that. Students are more alike than they're different in their cognitive processes. So there's some value to sort of old-fashioned teaching, right? You might do with that what you want. So I can talk a little bit about depending on what we want to talk about, right? I could show you a little bit what's come out of our process of doing many, many years of sort of iterative improvement. And out of that, but I should really mention that I wasn't the first to do this. So we learned a lot from the How to Design Programs project that Matthias Felleisen has led over many years now. And we kind of piggybacked onto its concepts, and there's now, so there's that. So if you speak English, that complete book is online. If by any chance you speak German, you can go to our website, and that book is also completely online. And so Matthias really did this, it says over 20 years ago, but I should really fix it to say over 30 years now this year, I think. So we ended up, so one of the outcomes of this project was that we would try to, so we and Matthias specifically, and us, we developed a pedagogic approach that was based on very similar ideas as this English class handout that you saw in the beginning, right? So we give, if you will, a methodology in the form of what's called design recipes. So we do a very systematic process from the problem statement to the solution in the end, right? This is not the only ingredient. I mean, you might have noticed that I kind of, so this is the pedagogical aspect of it, and I can go into depth with that. But one of the other things is, well, you might ask, well, if I said your favorite programming language is not right for teaching, well, what programming language is? And so one of the wonderful things that came out of Matthias's PLT project is they developed a programming environment called Racket that I'm sure you've heard of. And the great thing about Racket is that it's a toolbox for building languages, and specifically you can use it to build teaching languages. And so when we started developing in the early aughts, I think when we started really iteratively improving our course, we would just we would ship a programming language just as a library for Dr. Racket that students could install. They would give us feedback, and we would essentially, in the first couple of years, we would just ship new versions every 1 or 2 weeks based on that feedback. And so that feedback has now gone on for about 15 years, and hopefully things have improved continuously over that time. Having said that, there's still more room for improvement, right? So not everything I'm going to show you, if you like, is going to be perfect. So so these are languages. I mean, you can already see here that parenthesis-based, like schemas. This is probably not essential. It just means that both Matthias and I came from a scheme background, and you can probably evolve from different places also to something. But you're going to have to also spend 10 or 15 years on it to get to that place, right? So beware of what might happen there. So specifically with the teaching languages, the way they work, and I can show you later, is that there's several levels. So during the teaching language that we start with is highly restricted, and we kind of open it up and add more features as the class grows by switching up a level, as if you were sort of in a video game or something like that. So we have like 3 levels. So the teaching languages grow as you learn more. We try to make the programming environment provide feedback that is helpful to students, right? And there might that might ring a bell with you, that the feedback of your favorite programming environment, your OCaml or Haskell compiler, I don't understand it half the time. And I've dealt with this long enough. And also we designed the languages to have a one-to-one mapping to the concepts. And as I said, we've iteratively improved that over many years. So the pedagogy is based on what I like to call systematic design. So it has an explicit methodology rather than an implicit one where we give you a bunch of examples and then you're supposed to figure it out yourself. It emphasizes, and I'll happily show you that, in excruciating detail. It emphasizes not just the program being correct or giving the correct result, but having the correct form as well. This is very irritating to a lot of folks. So it's not so that matters as well. As I said, and again, that pedagogy has also been iteratively improved over many years. There's many publications on that out of Matthias's group, out of our group over the years. And it does, I cannot emphasize enough that it does not at all stress being excited or passion or something like that. It does not stress that at all. In fact, historically, I mentioned at the beginning that I really used to stress passion and excitement, and so we weren't happy with the results. So from one year to the next, we removed any kind of passion or excitement we could find in the class systematically. There's videos of that. I don't smile in the class. I cut my hair short. I put on a suit, and things got, and we changed a couple of other things as well. But first of all, things got better as far as people learned more. But also the class was in teaching evaluation was just as popular as before. So the passion hadn't made a difference at all, right? So it was very bureaucratic, and students sometimes feel that bureaucracy in the beginning and complain about it. So I'd like to warn you, if that's something that you're interested in, and you look at, for example, how to design programs or our book, you will find that it is super, super pedantic, right? But remember, you're not the target audience, right? The students are the target audience. That's very different. So it's not a book that you're going to come out of saying, I love this book, the way that you might be with the MIT book. So they're based on something called, I mentioned that they're based on something called design recipes, which are explicit name techniques. If you're interested, I think it's better that I show you, but really they're very bureaucratic in many, many ways, right? So you're really supposed to do steps in a certain way. Having said that, so really, giving this talk to a larger audience, I should point out some of the main differences between approaches to teaching that a lot of people find compelling, right? That are usually based on some kind of passion, excitement, constructionism-based idea. So constructionism says learning is an individual activity, and we're more focused on equitable teaching. Constructionism says, well, we just give you the tools and material. Program by design says, no, you got to do things a certain way. Also, something I haven't mentioned is that constructionism works by having motivating examples. And of course, being in functional programming, we connect a lot of things to algebra. In particular, the How to Design Programs curriculum has a high school offshoot, which focuses very much on the parallels with math class. So I can report on their results, but I'm not really an expert on them. That doesn't mean we completely do without things you're motivating. So for example, in the university class, we usually, students usually about halfway through write, I was going to say 80s style video game, but you have no clue what that is, right? So anyway, students learn soon enough. Anyway, so you can write video games as they were in the 1980s, arcade games. You can write them using Dr. Racket, and that ought to be motivating, but it's in the middle of the class, not at the beginning. So I mentioned that high school spin-off. So this thing that I could tell you about if you're interested, or that we might have a conversation about, really is something that, that Bootstrap project is doing that from 5th grade on up for high school students. We now have a lot of experience doing that at the university level, at universities in many different countries, specifically at a lot of universities in the US. And strangely enough, when I transitioned to industry from academia, and people would commission like 3-day classes on functional programming or in a specific programming language, we found out, and we really should have known, that the best way to do that is to do the exact same thing as we did with introductory students, only much faster, right? With all the elements that I just mentioned. Okay. So, so this is kind of the intro remarks that I have, with a lot of intro remarks. Right? Does that? Okay. Does anybody have any questions so far, or any remarks about that? Yes.
When you do this with students from the industry, do you still use Racket?
Yes.
Do they not complain about the
No.
language or anything like that?
No.
Because my suspicion would be that they'd be prejudiced to the surface syntax of the parentheses.
Well,
I mean, no, I believe you. I'm not just
I mean, the point is, so let me expand a little bit on that, right? So when we started out doing commercial training, right, people would come to us and say, well, we want an F# class, or an OCaml, or I don't think any of us ordered an OCaml class yet, or a Haskell class or something like that, right? And our thinking was, or my thinking was, that we're just going to use the pedagogy with their programming language of choice. Now, of course, you can do that, right? My thinking was, they're used to complicated syntax. They know what that works like. They're used to incomprehensible error messages. That's not going to faze anybody. So all of those advantages of the teaching environment maybe are not so important to the professional programmers. And it was okay, but it wasn't great. And as with many other things, right? I then figured I might as well try out something else, right? And so when somebody these days orders an F# class, a Haskell class, an Erlang class, or something like that, they order typically commercial training in Germany, typically for budget reasons, usually 3 or 4 days. So when they order a 3-day training, I would do an introduction to functional programming using those teaching languages for 2 days, and then transition to the language that they ordered on the last day, right? Of course, people complain, but remember how I said I'm not doing a passion-oriented, you have to like it class? Specifically, a strange thing usually happens on the 3rd day when they realize that the parentheses rules and whatever programming language of choice are more complicated than they realized, right? And then it has its advantages. I'll tell you all about if you don't know what I'm talking about, right? But these teaching languages based on Lisp have extremely regular parenthesis structure, right? And then we can have an argument about this. But even both with university students and with professional students, right? I found that it really sets the stage correctly to say these are teaching languages. They're just there for teaching. You don't have to worry about, is this professional grade, whatever, right? We can have then a nuanced discussion about those things. But it's very clear to everybody these are just teaching languages, and that we found over the years helps a great deal. I don't have to defend anything, right? I can honestly say these are the languages we've developed for teaching, right, with students like you over the years, and we've improved them. And so you weren't there, right? So and they tend to believe me, apparently, if that answers your question. Okay. Any other? Yes.
Would it be easy to also go to some of what are the features or characteristics of Dr. Racket that make it a good teaching language?
So I can show you, right? So I think better to show you. Okay, but you wanted a summary. I think I have that. Didn't I have that somewhere? So here's a screenshot from that. So let me summarize, and then you can tell whether you're interested in the rest. So first of all, the UI is very simple. So if you've tried teaching with a professional IDE, you will find that there's a lot of elements that you can't really explain to students because they lack the terminology. This is a general phenomenon, both for the language and the UI that you're using, right? Is that there's just, you stumble into territory that you haven't learned about yet, and then you don't know what to do, right? So that, first of all, is a case for the UI. So the UI is very stark, in that there's just a program window at the top, and then there's a REPL, an interactive thing at the bottom, and you just push the run button in order to start the program, right? So that's the UI is just very simple. Doesn't have a lot of elements in it. Another thing that's helpful, but probably not as helpful as you think, right? It's just the fact that there's this REPL thing, so you can try out things interactively, and that makes a slight difference as compared to very static languages like Java or something like that. But it's not that important. That was one thing. So then I mentioned, well, just having the ability for us as teachers, right, having the ability to incrementally ship a new release of the languages every couple of weeks was crucial. We didn't realize that that was a thing while we were doing it, but imagine, whatever, hacking on GHC, shipping a new version, just explaining somebody how to install it maybe I should backtrack. One really nice thing about Dr. Racket is everybody can install it in 5 minutes, right? Including the IDE and including everything, no matter what your platform is. That's also important, right? In a class, it's no big deal. Well, it's a deal, right? I sometimes teach Haskell-based classes and just getting everybody, even with Docker containers and everything prefabricated. Usually you spend a half hour making sure that everybody's stuff is installed. So as far as the languages are concerned, another factor is that, well, you can't see it on the screen, right, is that because we have these stratified languages where you just have a little language at the beginning, right, I mentioned that if you use a professional language, then inevitably you stumble upon an area of the language that you haven't covered yet, right? So you make a curly brace, whatever, or something like that, or if you're into Haskell, right, very soon you'll get an error message mentioning type classes. It happens very quickly, right? As an example, and usually you don't want to explain type classes at the very beginning, or I don't know how to do that anyway. So it gave us the ability to do that, and it gave us the ability to really customize error messages, and again improve them iteratively as we got feedback from the students, right? When they would say, when they would be puzzled and say, "What is? I'm reading this, I don't know what it means." And the languages themselves were, so one feature of the language that is kind of inconspicuous is that you could intermingle the program with test cases. So testing is an important part of the design recipe. Whereas, think about your favorite unit testing framework. You've got to create a separate file. You've got to, I don't know, compile a runner or something like that. Right here, you just press the start button. And you can write the test at the exact place where it occurs in the design recipe. Right? That's another advantage. So generally, we've just made those languages, and I'll go into more detail if you like. We've made those languages to then match the pedagogic concepts so they've co-evolved with the pedagogic concepts that we've developed. So does that answer your question? So first pass over it? Yeah. I mean, if you're, I don't want to diss on Haskell so much, right? But the Haskell educational people, right? If you look at history, there was an educational version of Haskell called Helium, which is also based on taking things out of the language, based on that very same observation, right? Is that students get confused because they stumble upon stuff that they don't know about yet, right? And this is just this thing is greatly reduced, and this turns out it's also something that helps professional students, right? You don't have to do all of those things at once. Yes?
You have a specific example of the kind of feedback that is essential for students and that you implemented in their own messages?
Yes. Okay. Now, is it okay if I just fire it up and show you a bunch of stuff? Version, it shouldn't really matter. Fire up.
Actually, asking for examples in that methodology.
Well, but I mean, the thing, again, let me maybe I should have different colors here. No, this is fine. I don't know. I don't. So I've harped on about doing systematic development of programs. I don't know how to systematically do all the pedagogy, right? And as you can imagine, over the years, I've talked a lot to the didactics people as well, with interesting feedback I've gotten over the years. Let me kind of. So the way that you can do this is you can. So I'm just going to talk. I should mention that Matthias's teaching languages and our teaching languages are different, right? And so I'm just going to, ours is, it's a Germanism, it's a Dyn program, teaching languages, and the book is called Schreibe Dyn Program, so that's SDP up there. You can also select it via the UI. So one of the things that's important, so first of all, I'm not being very systematic here. The most important part of the design recipes is something called data analysis. So you look at the entities that occur in your problem statement and you create a systematic data model. This has, I cannot tell you how tremendous the value of that is, not just sort of as a pedagogic instrument, but also as a professional technique that you use for developing that a lot of people don't know how to do. So, and the data analysis then says, well, you translate your data definitions, you translate that into code, and then you write functions that operate on it, right? And so I need to skip ahead like a bunch of steps. So, and usually what would happen is you would write, so for example, your data analysis. Let me do one example. You're gonna have to be a little patient if that's okay. Okay, and you just kind of, so here's the classic example. So the PLT group, Matthias's group was originally based in Texas, and they said on the Texas highways, there's armadillos, right? And so you might start with something like this, right? An armadillo is dead or alive, and it has a certain weight, okay? So you might kind of sketch it out like this. Now, the design recipe insists that you classify what kind of data you're looking at, right? And and you do that by looking for certain wordings, right? And one wording is, you might say, well, you could try out one wording to look for. If it applies, you could say an armadillo has the following properties, right? If you can make this wording work, then you are dealing with something called compound data, okay? This is a no-brainer for you, but of course, there's not just compound data. There's also your discriminant sum or sum type or whatever it is. We'll get to that later. Lots of people, lots of professional programmers don't know how to deal with that, just as a, right? So anyway, compound data. So the idea then is that you write this out and you translate it structurally in a way that corresponds recognizably into code, right? And so in the teaching languages, what you do is you create what we call a record. So you say define something called define record, and you say, well, I'm just going to abbreviate armadillo. And what you do is you say, well, I'm going to define something called dillo. I'm going to define a constructor, and in the constructor, I'm going to make this easy. So I have one clause for each component of my compound data. So I'm going to say alive, that is a Boolean. We'll later get to what all these things are. And I'm just going to say the weight is a number. So something like this, right? And this will give you, so this record definition will then give you a record data type, if you will, right? And you can call make dillo, and you could say, something like this. And this would be, an armadillo that's still alive and it weighs 10 kilograms. There's a couple of things subtly wrong or not quite right with this, but it's good enough for now, right? And so I could then create examples from that. Now, dillo 1, make dillo, right? And I could write a comment, also part that relates the information to the data that represents it, right? So this is a live armadillo. 10 kilograms or whatever the unit is. So obviously that is an issue here, but we'll get to that later. Now, first thing that we always do is we say, well, it's a tough world, right? In Texas, so the armadillos get run over, right? So you have, run over an armadillo. Now, so you've got to write a function that represents that, right? And so you might go, run over dillo, something like this, write a function, and it goes, well, here's an armadillo that goes in. And I should really have written this here. I'm a little bit sleep deprived. So these are the selector functions. And I'm now going to say, well, I'm going to make a new armadillo object, and it's always dead. And it has the same weight as the ingoing armadillo, right? And so we can do that, and then we can go run over dillo of dillo 1. Oops. 1 down here, and it will give us one that's dead and still weighs 10 kilograms. Okay. So anyway, so I glossed over a couple of things. So first of all, what we ask students to do is we ask them to write what's called a signature. So first of all, to think about you're writing a function, what data goes in and what data comes out, right? And so in Matthias's version, it used to be called, I don't know, I think it's called a contract signature now. So he would say, run over Dillo, and he would write a comment that would look like, might look like this, right? Might look like Dillo, arrow, Dillo, or something like that, right? So, but it's a comment, okay? So, and one of the things that we realized is that students, well, and this is a mandatory part of the design recipe. So if you don't write a contract, then you don't get full credit for your solution, right? And so, we observed then that students were getting really, really sloppy about those signatures, right? Sure enough, they would write functions that would go like any, arrow, any, or something like that, right? They would get sloppy. They would also get sloppy with the syntax and so on. And of course, they would never get feedback. If they violated, the system would not give them feedback on that. So what we did is we made the signatures part of the language. That's maybe really the most conspicuous example where we made a specific change. So you write this, looks like this. And now you have a signature that looks like a type signature. It actually isn't something that gets checked at runtime. So if you go and violate it and go run over Dillo, you kind of misunderstand how things work. So you get something called a signature violation, right, down here. So the program fails, but it doesn't just fail. Along the way, it tells you, well, here is a place in the program, that place in the program. These are clickable links down here, by the way, and you violated that signature up there, right? So that's one of the things that we added specifically based on student feedback. Strangely enough, what happened is when we introduced this, right, the students, records, are this thing where you can see it's a complicated syntactic form. This is right. This is like 6 weeks, 2 months into the class usually, so this is not the first thing that they see. But there's a couple of things that need explaining, right? What is this make Dillo thing, right? That's the constructor functions. These are the selector functions. These are whatever, blah blah blah. So there's a number of things that you need to explain. And well, one of the things it does, well, it defines 3 functions, right? Make Dillo, Dillo alive, Dillo wait, right? And we found, so, out of, when the students were puzzled about this, I said, well, you can just write the signature here, and you can see that the signature, and here you can also see what that Dillo thing is, right? That Dillo thing is also a signature that was newly defined as part of that defined record. So now, and we just tell students at the beginning, for the first couple of record definitions, you always write the signature of the constructor. And you might also write the signature of the selector, right? And of course, now you've got that same information in triplicate here, right? You all see that this is redundant, right? Strangely enough, the students were going, I was like, yeah, well, this is all redundant information. I'm just going to do it this once. And they were like, no, Mike. You said be systematic, please, and they made me write it out for quite a while longer than I normally would have. And this is also, well, this required a little bit of implementation effort to not just be able to write signatures for your own functions, but write functions, but also be able to write signatures for the functions defined by defined record. So that's maybe a good example. We did a paper on that years back. I don't want to miss it. It's so much so that it's even, we ported this feature also to Matthias's teaching languages, even though it's not used in their book, but it's there in the language if you don't use it. Right? So that would be an example. Any other questions? Went off on a tangent there. Yeah.
Can I just sort of play devil's advocate? And
say, yeah, absolutely.
Well, this is more or less what I would do in Haskell anyway.
Yes. Well, so as I said, right, starting from Haskell, you might be able to do a serviceable teaching language, right? That looks like Haskell. I think you would probably end up taking out type classes, adding them later. You might find some other approach. You could certainly do these things, right? But getting that to the same level that these languages are would just take you a couple of years, would be my guess, right? Just because the feedback cycles are so long. So I'm not saying you can't do it. You could absolutely do it. I mean, you can certainly quibble with the syntax. So one of Matthias's students, Sriram Krishnamurti, I don't know if he's going to be here. He developed a sort of teaching language based on many of the same ideas, but with indentation-sensitive syntax, just like Haskell, seems to work fine as well. So those are not, I think very few ideas are fundamental. But let me suggest one thing that I found difficult, and that might just be due to me, if I teach Haskell. So from the days when I tried to teach Haskell or F# or something like that without that basis, Haskell has this algebraic data types, right? And which is one construct that conflates several things, right? Both compound data and discriminate sum types. And you need to do this tagging, right? And that's quite a bit to do at once. And I haven't found a satisfactory way to do that that immediately sort of produce successes with the students. On the other hand, explaining it in terms of what we do here is has been much easier. Let me explain what I mean. So as I said, I mean, I'm not, it would be wasted effort to just try to explain to you the whole didactic approach. You can just read up on that, right, in one of those books, or send me an email if there's anything that we're missing. I mean, we still have quite a bit of time. So you get to that point where you go, well, the Texas highway, it's not just armadillos, right? There's a second kind of animal. And you go, I usually do parrots for some reason, right? You go, a parrot, right, has the following. And note that, you know, this, what I'm writing here is the result of a small process that you're doing in order to analyze your data. But it's so these are all talking parrots, so they all have a sentence and they also have a weight. It's actually turned into quite a nice Haskell example as well at some point, right? You go translate that into, I mean, as I do this, please be aware, right? I mean, I've said this, but really me just kind of glossing over it does not prepare you for the excruciating bureaucratic detail that this whole thing goes into. The level of, you know, pedantic process is just really, really annoying, I think, when you're looking at it first, but it's been really, really effective. And where, I mean, when we do the accelerated version with professional students, this is also exactly where the weaknesses are, right? Where you find that we haven't had enough time to really to beat that bureaucratic process into students, okay? Right? So just know this, right? There's a lot of bureaucratic detail here, just mind-numbing level of detail here, right? And so I'm just glossing over that. So we're going to do, hi.
Sorry,
I mean,
the camera is frozen.
Okay,
Aaron, can you just refresh the page?
okay.
Just
Okay. Okay. So we want the entire screen. Should it come back?
yeah, your camera is not on.
But so now it's off and now it's on, but it didn't come on, right?
Well, then they'll just hear you.
Okay, my face is not that interesting anyway. So when I'm mostly here over to the side a little bit. Oh, no, that's fine. So, okay, good. Great. So we got make parrot, right? And you can already see this is like going in the same direction. So we go parrot sentence, parrot weight, some kind of number here, right? And then we play with parrots for a while, right? And then you go, well, at least let me do, I mean, no. So just to give you an idea, some elements of a function, what we call a template for a function. So as part of a function definition, you're supposed to write a one-line comment, just one line, right? So this is something that everybody can do, right? So you run over a parrot, right? One line. Then you write the signature and you go run over parrot and you go, well, parrot goes in, parrot goes out, okay? Then you are supposed to write a couple of test cases, right? I'll just write one. Maybe as here, we should have written an example. So we have a parrot that says hello, and that weighs, I don't know, 2 kilograms. And we are going to expect that when we run it over, that parrot, then you want, parrots shut up when you run them over, right? So you go there, right? And then you go, okay. So now note that, you kind of successfully think a little bit more about the problem on each step. So one of the things I think that I didn't mention, right? One of the issues, especially at the beginning of a programming class, or at least for me in Germany, was that students get stuck, right, at some point, right? They don't know what to do next. And the design recipe always kind of gives you an easy step to do next, right? And preferably that step is completely mechanic, right? And then to their surprise, the students find out that the last step, which is kind of all the kind of creative steps are at the end, they find out that the last step then is pretty easy, right? Amazingly. Students are really surprised by that, I think, because you're not used to being able to do something complicated successfully on their own. So what we do here is, so people think about the signature. By this time, they already know the name of the function that they're writing, right? And so as the next step, they go and say, well, I'm going to go, let me demonstrate some bureaucratic detail. They already know that this function might look like this, right? Right? So the define, there's always a define, there's the name of the function, there's always a lambda. We need a parameter that works, that is compatible with the signature, and then we put 3 dots here. We call this, we have slightly different terminology from Matthias, but we call this the skeleton. This is a thing, right? And in class, we would give credit for this, including the 3 dots. Okay? So this is, I'm just going to call this the skeleton, and I'll comment it out just to document that it was there. And you get credit for this, right? You get credit even if you didn't continue after this. So here's the whole thing. The next thing that we do is that looking at the signature, right? We can infer from the signature some program elements that probably go into the body of that function. A parent object goes in, it's compound data. Usually if you want to do something sensible with a piece of compound data, you need to look at the pieces. So what we have is we have people, without thinking, write down the elements that they can infer from the signature. So they are supposed to write parrot sentence of parrot. And they write parrot weight of parrot right here, and put 3 dots there to mark the gaps. Also, parrot occurs in the output, so they probably know that they probably need to call the constructor. So they write that, and the constructor call is kind of like a form that you need to fill out. So they think then, well, so what's that sentence that the parrot needs to say, right? So parrot shuts up, and then they go, oh, well, the weight is the same as before, so they go down here and kind of move this from here to here, and then they're supposed to think for a little moment and say, well, what happened to the old sentence of the parrot? And then they go, well, and then they're now supposed to think a little bit about the problem. They go, oh, right, yeah, if I run over a parrot that's already dead, that doesn't change anything, right? So this is what's called the template. This is kind of the most important part, really, or the most helpful part. Again, neglected to document it. Do that. So here's what's called the template. So this is this part here. Okay, and then here is then the finished function where we remove this and kind of clean it all up. And now I wanted to comment this out. You get German error messages that just says for this name, there's already another definition because I define it twice. And now it says, oh, the test passed. Okay, so there we go. So the translation infrastructure is one of the things that's up for improvement because there's not always points where you can provide a translation. So now you go, so far so good, right? So lots of bureaucratic detail. Now you go didactically, you kind of go, well, you get up on the wrong foot in the morning, right? You didn't sleep well. You're just going to run over the very first animal that it doesn't matter. It's a parrot or an armadillo or something like that. So we need a new definition, which is an animal, not just an armadillo, an animal on the Texas highway. So you kind of go an animal, and recall that we had this same thing where it said an armadillo colon something, right? And here you go, an animal is an armadillo, or it's a parrot, right? And now we encourage, again, people to look for the right wording. If they say an animal has the following properties, that doesn't make sense. So you go like an animal is one of the following. That makes more sense as a formulation. And also you can encourage people, if you're into duality, of course, you can kind of encourage people to kind of go up here and say, well, your parrot it has a sentence and a weight, right? And you can go, well, an animal is one of the following, armadillo, an armadillo or a parrot, okay? And the idea is, again, that and this is a separate idea, right? To have this or construction that we call, I think is for historical reasons, not a super name, but it's called mixed data, is what we call it. And then you can name it whatever you want in the programming language that you get to. And and of course, because now this is a different kind of data from the compound data, you translate it into a different kind of programming construct. And the way it works here is we go, well, we already have, there's nothing new here, right? We already have armadillos and parrots. So all we have to do is we have to declare a signature, we're just going to call it animal. We have a signature that's mixed together from armadillos and parrots, right? And then you can have, we'll go in just a second, we'll go into program with that, right? Now notice, again, part of that excruciating detail is they're encouraged for students, for example, to go count how many is there here, and it should be as many as there are there, right? You would be surprised how often that goes wrong, right? There's a mismatch, right? You go, how many components they go, there's always an exercise you with, I've got my digital watch and I go like, there's hours and there's minutes and there's seconds. How many parts is that? They go 4, right? So, this, and I'm like, what's the 4 coming on? Hours, minutes, seconds, and the time. So these things, I think they seem obvious or trivial or simple to us, but for example, the stuff with the compound data is absolutely the hardest part. Everybody gets over that hump, but it's the one that requires the most work. Surprisingly, recursion or something like that is not, right? That's something everybody gets over reasonably easily, but we can talk about that too. So anyway, so here's really important that people can see, ideally they would structure it this way, so that we really see armadillo, parrot, and things would match up, right? So, and this is generally the way that we've tried to design the teaching languages to enable that correspondence. Now, going back to your question, right? Going back to Haskell, right? These things, the mixed data and the compound data is one construct. You have to write it as one. You can't, after the fact, put parrots and armadillos into a subtype without adding another level of tags, and don't even try to, that does not work didactically, right? On the other hand, if I have this, I can then go, okay, look, at this point, right? Imagine us having taught 2 days of this, right? After 2 days of this, students have they've noticed that quite a few times we've seen there's mixed data off where all the cases are compound data, right? And then we can go, well, in Haskell, they've recognized the fact that this is a frequent programming pattern or whatever you want to call it. They just made it into a construct. It's called data. Here's what it is, and it's super convenient. And that's, in my experience, worked quite well. So that's why, that might give you a glimpse of why I prefer doing this first rather than jumping into the programming language of choice. Yes?
I have a question. So which parts are checked automatically, like the comments and the description, and which parts do get checked by a human at the when they're writing an exam?
An exam?
Or when somebody gives them points.
When somebody gives them points. Not sure I know. So
just a rough idea where we are.
So of course the syntax gets checked, right?
Yeah.
And it tells you that your test case is passed. And it tells you whether the calls in your test cases in the code that you added were conformant with your signatures, right? You saw that it gives you a signature violation error message if you do that. What it does not do, and arguably it should, right? It does not, for example, automatically check that there are test cases. So Shriram's language, I think, doesn't even let you, it only sort of, I think it write protects the place where you write the function until you've written your first test case. You literally cannot write a function before writing the first test case. So we don't enforce that, for example, right? And of course we don't, generally don't enforce things like naming conventions and the signature thing is completely optional, right? You can leave that out as well. So if I just comment out that, I mean, you've probably noticed that in the beginning, right? If I just comment this out, then the whole thing will still work. You just don't get signature violation. And arguably, there's a point in the design space where you do more checking. It's just that historically, the path that we've taken is this one. Right? So there's a lot of, I think Matthias's group, arguably, you could also generate the template automatically, right? Right? The way that you can fire up Idris or Joachim Breitner's thing, whatever it is for Haskell code, right? And I think there used to be a prototype of that, but I mean, don't forget that. I mean, I'm sorry.
There's some value in writing.
There's some value. I mean, we shouldn't forget that sort of the human brain, sort of from an evolutionary perspective, right? We learn by our bodies moving through space. Now your finger is moving across the keyboard is kind of a poor proxy, but it's better than nothing, right? So that would be my explanation from this, right? But you're, again, on all of these things, right? I mean, I'd be delighted if somebody said, you know, we tried your thing, but we tried a slight modification. So for example, going to your point about Haskell maybe, right? Thorsten Ghost, who teaches this class at Tübingen, who's also a great fan of Haskell, said, you know, Mike, what I really, really like is pattern matching, right? Because this is like super, and I don't share his opinion, but there we go, right? I mean, this gets super annoying, right? Or it gets a lot of, or people tend to get, well, they don't, I mean, beginning students don't know anything else, so they're fine. But of course, you can imagine your Java professional programmers who are trained in Java thinking, I can just use dot syntax, right? And they even Stockholm syndrome the Haskell people into thinking that that's a good idea, right? So Thorsten came and said, you know, I really, really, really would like pattern matching. So I put a pattern matching thing in there. I can demo it to you in a second, right? And he says the class, and he taught the class with selectors before, then he switched to pattern matching. Seems to work. He's delighted. So modifications, changes that you might want to make, are always welcome. I mean, there's lots of room here, right? Or you can just fork off those teaching languages and create your own, shall we? Okay, maybe I can show that to you, right? So now we've defined animal, right? And we said we want to get up in the morning, we're really angry, right? Drive angry. So we go, well, we want to run over an animal. And here's also right here, also here the Haskell thing breaks down. So you go, we'll run over an animal, animal in, animal out. This, by the way, is something that works well to explain, you know, the shift from imperative programming also to the professional programmers. And then you can go, yeah, we'll run over animal. If I run over Dillo1, that should be the same as using that specialized function. Should be more test cases. Now, so we have this, right? This is the skeleton. And because we're now dealing with not compound data, but mixed data here, a different template applies, right? And the template that we usually use is this one, right? Where we go, well, we insert a conditional. And then we go, well, your conditional has branches, and it has exactly as many branches as you have cases in your mixed data, right? And so you go, just to show you how that works, and we start by really putting lots of dots in here, and we've introduced conditionals previously for number ranges and so on like that. The thing is now what do you write here to tell apart the armadillos and the parrots? And at this point we go, well, we need, so right now we can't, right? We could with pattern matching, but the way it works here is that you can write another name here and that becomes a name of the predicate, right? And then we can again explain that in terms of a signature that says, well, anything goes in and a Boolean comes out and tells you whether your whatever your value is really an armadillo object. And the same thing happens here, right? Where we do this in, and so the template would be this, right? Where you go dillo animal and parrot animal. And we can nicely then just call the functions that we already have, right? And this would not work in Haskell, right?
Okay, but
Right.
it's more like a dynamic typing versus static typing.
Well, I think it.
Because it's the question of
Yeah.
whether the tag is in the mix.
Yeah.
Or
So-
in the
Yeah.
the animal.
Yeah, so that's a good issue. So that's a perennial question, right? If error messages are important, right? Why is this language dynamically typed?
No, I'm
No,
not
it's not.
criticizing.
Huh?
it.
You don't
It's-
have.
but-
It's a perfectly
What
fine
I'm
to
saying is
criticize it.
that it's not a question about whether you couldn't do this in Haskell. You could do it, but then the tag would be in the mixed data.
Yeah.
You have an extra either or something.
Yeah.
So it's the question of this way that the tag is in the any, the object. You ask it whether it was formed by that construction.
Yes,
So
absolutely.
it's a dynamic type.
Yeah.
approach.
So yeah, but let me justify it anyway, right? So funny that I'm going to say the word example again, right? But it's helpful to students if their program goes wrong in the sense of violating any of those signatures. It tells you here's the value, right? The program came across a value that was supposed, and here's the value. And that tends to be more helpful than a type error message, which just says, well, these two expressions the types don't unify or something like that, right?
That's fair.
But on the other hand, notationally, of course, this is already very close to types, right? And so one of the things undone that's on my plate is, of course, there's a typed version of Racket, right? As add another language level that just takes the same program and interprets the signature at the value signature, interprets that at the type level. See how that goes. That might be interesting, right? On the other hand, again, having done all this and then transitioning to Haskell has usually been a pleasant experience, and I'd be happy to go over that as well. Anyway, but just to show you, so you could do this, but you can also go match animal, right? And could write, it'd be a slightly different way of writing it, but you could go, well, here's a match, and you could go, well, if it's a make dillo alive and wait, you could go make dillo false and wait. So you just, very similar to the way it would work in Haskell. So, and then go, so, and that should also work, hopefully. Yep, also works. So, as I said, Torsten Booth is very happily teaching this throughout. Saves him he then does not have to introduce the predicates, right? So there might be an advantage there. Okay, the other jumping around a little bit. Maybe we can be more systematic in the second half, but any other questions or issues?
Yeah. Are you faced with students that feel like disappointed or frustrated because you make them use a language that they consider is not a real language used in big companies, and therefore they have the impression of not doing real programming? Because that's a
So a short answer is no. But this really, I think, has to do with, I told you the story in the beginning, right? The year when I started wearing a suit was also, and I said, we removed all passion, excitement, and positive motivation from it. And then as I think many universities do, we have like a student evaluation of the class, right? And a funny thing happened, right, is in a year where I spent a lot of energy on sort of putting a positive spin on this great language that I was so excited about, students put forward exactly the complaints that you just mentioned. Once I put on a suit, I don't think I even said functional programming even once in the class, right? I said, these are teaching languages, we're teaching, that's it, right? Deal with it, right? All those complaints disappeared. And with professional programmers, as I said, they sometimes quibble with the parentheses, but then they kind of quibble back when we move to, or when they figure out that really parentheses aren't that easy in their programming language of choice either, or that it's not so easy in Haskell or in Scala, God forbid. But generally not so much, right? But that might just be due to time passing, right? And so the wider, even in Germany, I think, which is backwards in many regards, the wider developer community knows that functional programming is a good idea. They've seen functional programming features migrate over to Java, right? And they figured it out by now, which is very different from 25 years ago when all of these things were far more exotic than they are now. Right? And so it might just be that and not my change of teaching approach that made the difference. Might also be a cultural issue, right? So in Germany, we have a saying, so Germany, soccer is very popular, right? And so the German conventional wisdom is that there are 80 million national coaches, 80 million people who could be a much better national coach than whoever is in place right now. And so that might be true for teaching computer science to 19-year-old white males as well. Sometimes. Yeah.
You talked a little bit at the beginning about like kind of initiatives for children trying to get like young kids excited about programming and stuff.
Yeah.
Do you think any of this approach is like carries over to that side of things as well? Because it seems very different, like trying to engage someone and having a very mechanical approach that gets rid of all the excitement.
Yeah, I don't know. I mean, I really don't. I have not figured out a bridge yet from here to there. And I mean, there's difficult issues with that, right? So, I mean, if you're dealing with smart kids and they love this other stuff, right? What should you? I don't know. I don't know what to do, right? On the other hand, so I think for the time being, these things I think are best treated as two separate things, and I think a lot more communication and maybe research needs to happen in order to find out how to maybe combine things from both worlds, right? But I mean, I'll say this, right? I mean, despite the fact that in my latter days at the university, right, we taught without passion insofar that's possible, right? It did not seem to diminish people's opinion, right, of how things work. They liked it just fine. Right? So in my so far conclusion over this, right? I'm not a psychologist, I'm not a didactics professional, and so on, right? Is I think that I mean, I'm sure you've heard, right, that in didactics, something called intrinsic motivation is better than extrinsic motivation, right? And that would make it seem very obvious that forcing your students to do things a certain way would be terrible, right? As opposed to telling people why they're doing what they're doing, right? This seemingly goes against didactics wisdom. I've had lots of discussions up in the didactics conventions and try to work this out. But I think people get wrong what good intrinsic motivation is in this context, right? My impression has been, again, this is just so far wisdom, right? Is that students they like being able to do complicated things on their own successfully, right? That is what motivates people, right? And all your good explanations, all your promises that things are wonderful, they don't mean anything to students, right? The context is missing. You're just some other person to them, right? And so I think ultimately, and so the difficulty then is to get students to that point, right? Where they realize, oh my goodness, I can do this, right? And my very consistent experience with German students has been that they've never had that experience with sort of mathematics-related subjects, which this programming stuff is, right? A lot of them have not had that experience of being able to do something complicated on their own, right? And so you really have to, so we always have the impression at the university level that we really have to kind of kick them and push them over that finish line. Well, it's not the finish line, but the first finish line in the first couple of weeks. And then they realize, oh my goodness, right? This stuff is helping me. And that provides the intrinsic, so up to that point, they're not intrinsically motivated. I don't know how to do that, right? But then it seems to generate its own momentum. So if you look at our homepage, you'll see lots, well, not lots, but a few papers that we published on the results of kind of that switch that I just told you about, right? And so, same thing, the next professional say, well, one of the fundamental tenets of education is, well, you should be able to say, well, there are several solutions to your problem, right? We should be able to contrast them. What do? We tell them, no, you've got to do that one, right? It has that specific form, and therefore it's pretty much, except for the choice of names, right? The correct solution always looks very, very similar, right? And I think that is more of the same, right? Your average student left to their own devices gets 0 solutions. There's no point in trying to, like, you don't get 3 that you can compare, right? Once you've gotten over that hump, that students are able to do stuff successfully on their own, once you've gotten there, you can do all of those things that are didactically desirable. But up to that point, you don't, right? And I don't know how to do that, right? The only way I've known how to do that is to somehow tell us, well, you do this or you don't get credit. So as disappointing as that might be. That makes sense. Okay. Any other questions?
Are you going to talk about how you get over the hurdle of recursion?
Yeah.
in the second
Yeah, my
part?
pleasure. Yeah, we can do that. That'd be something. So should we get to the tea like 3 minutes early, or the coffee, or the pastry,
For everybody else?
and then we'll get, that there's stuff left, and then we'll reconvene if you like. Here, I think in a half hour. Is that it? Right?
Can we have a little?
I'm sorry about the question that the students that were frustrated, because I was asking this question because the teachers at the university they actually used this criticism made by the students as a reason not to use Racket anymore for introductory classes, and that's
Yeah, but you don't have to apologize for that issue. Yeah, I mean, as you can imagine, I'm well aware of the political dimension of that debate. I've gone through that. And we went through bitter versions of that in the 90s, right? And I think ultimately, I mean, mostly you're dealing with, you're not having an honest debate most of the time, right? I mean, there are things to be said, but most of the time, people already know where they want to go. They don't like your Racket thing, or they don't like your whatever thing, right? And they'll look for arguments wherever they can find them, right? And I remember when that debate was going on at the University of Tübingen, right? It was some version of that, and if it wasn't a version of that, it was something else, right? Mainly, I think, because the other professors just weren't familiar with this and didn't know what to do with it and didn't want to find out. And so I think that argument, I didn't know it at the time, is ultimately futile. There's just no winning it. I mean, if you play on those terms, there's just no winning it. And it kind of we just kept doing our thing, and the others all went away. That's all I can say, right? It took a lot of patience. But I think, yeah, I'm not sure if anybody had any additional insights or something like that. It just, the problem kind of gradually died down over the years. And maybe it just takes a little patience. But it's a shame to then, it's a shame that was the basis for some kind of decision. I mean, what I would do is, I think what I would do is very aggressive. What we would do, what maybe contributed to the eventual success that we had, is that we very aggressively communicated the success of our approach, right? So we would evaluate. So we would say, exam scores went up. This percentage of students passed. Compare this with the Java-based class, which only had 20% less or something like that. And nobody asked for this, right? We would just aggressively each year do a little session open to all the faculty and students, and I think that might have contributed a little bit to get in front of that stupid bus, which is so playing their game just doesn't work. It's kind of sad that this kind of thing is still going on. So as I mentioned, where I am, so the developer communities that I talk to have all gotten around to the fact that they would that functional programming is something that they like to do, and just mainly their management keeping them from doing it, or something like that. But we should really. Maybe one remark before we get to that recursion thing, just because it came to my mind. So there's a couple of things here that I don't know how to do, right? That be great if somebody could figure it out. So one thing is that something we'll get to as a result of that recursion thing, which has to do with iteration, right? And a simple explanation would be just, it's hard to teach because it's hard, right? But there ought to be a better way of doing it than we currently are doing it, maybe. But as far as imperative programming is concerned, right? At least we wanted, I remember, for the longest time, at least we wanted to explain the basics of it, right? That there's this idea that there'd be not just that a variable would just stand for a value, but for a memory reference, you could mutate it. Here's the operations that are available on it. Here's a couple of things you can do with it. But I think that really was a cautionary tale. So there's a section in Structure and Interpretation of Computer Programs, which does this through diagrams, which at the time I thought it was compelling, even though the diagrams are not constructed completely systematically. So we figured we were just going to fix that. And so we spent, 3 or 4 years trying to refine the section on imperative programming and assignment and mutation. And when exam time came around, we were always disappointed. And so, we became so frustrated that I figured, we would spend, 2 weeks of time on the assignment and mutation imperative programming section, right? I figured we're just gonna ditch that. We're gonna do something that I like. If it's not successful, right? As much as you'd like to make it work, right? The thing to do is then to remove it from your curriculum, right? And either try something else. Just do something else or try another approach, right? There's very little value in just redoing something that's failed, even though you wish there's some important learning outcome there. Does that make sense? Right? So we felt the learning outcome was important. We didn't know how to reach it. So I just figured I'm just going to do 2 hours of hand waving, no fancy diagrams or something like that, right? And we would then do the exam, essentially the same exam thing. Students got better than before, right? So I can't tell you why, right? So to this day, this frustrated me so much that I really just cut that chapter. And in the meantime, I see that Matthias did the same. So I think fundamentally, there ought to be a way to teach at least certain uses of mutation, things like memoization or something like that systematically, but I don't know how to do it. That'd be a welcome input. But one thing that we do know how to do is to do that recursion thing, right? And I think one thing that I haven't yet emphasized the importance of sufficiently yet really is the whole curriculum is around the idea of data, right? So up and down, and left and right, it's always about data. And if there's a second thing, then it's about abstraction, right? And so we have this whole taxonomy of data, right? We say that there's compound data, that there's mixed data, and of course there's a couple of variants and generalization of that. But really, we very much encourage people to look at the problem statement, identify the entities, and then really go through it and say, well, could you describe your thing by saying, is it one of the following? Or could you describe it by has the following properties? Or does it consist of these other things, right? And that directs you to what to do. I'll point out, this is something that a lot of professional programmers can't do, right? This is something that's notably missing. I mean, it's not just something that other curricula are not doing well. They're not doing that at all, right? So when we teach professionals, they usually do not know they usually have no conception of mixed data, especially those that tend to focus like doing enterprise-based database programming, right? So one simple way to describe relational databases is that they don't have sum types. And a lot of data models are created starting from the database. And so then there's, you get poor models because of that. So everything comes from the data. And that's also the secret, pretty simple secret. And it's really not my work. This is something that Matthias figured out, I think, really early on. So examples for recursion tend to focus on like the functions that are recursive, right? And we tend to do things like whatever, the factorial or the Fibonacci or something like that, around natural numbers, right? Arguably, the natural numbers have inductive structure, but students do not have that intuition. For them, the numbers are a linear thing, not a thing of nesting. So anything, so we avoid, so the secret is just to use other data models that do not involve numbers, but instead that inherently involve recursion, right? And so I think I'm just going to tell you the thing that really just plain works, even though it's a little bit boring, is you start by doing lists, right? So you go and say, well, here's, so we go, I mean, kind of, you get to a point where you say, well, okay, so all the data that we've looked at right now has fixed structure, right? You have mixed data, you have a sum of these compound types, so the structure is just fixed in size in particular. So we want variable size. You use a technique called a self-reference. So that's kind of how the didactics work. So here's how to do that. So first of all, we're going to do like lists, list of things, something like that. And then we say, well, so here is one possible definition how you might do lists of things that are of variable size. So you go, well, a list, and this is really something that comes down from, the skies, right? We all know it's an arbitrary definition, right? It just happens to be kind of a sweet spot in the design space, but it's arbitrary. But we nevertheless present it as such. So we go, a list is one of the following. And then we go, well, it is either the empty list or it is a cons list, right? And consisting of the first element, and rest list. And now the important thing here from a didactic standpoint is you go, the word list appears in the definition of the term list, okay? So you go, well, this is what's called a self-reference, okay? And well, this is the key towards just using sort of variable size structure, if you will. You can translate this definition very straightforwardly into code, right? You can see here immediately, here it says one of the following, and then you just have to, if you want, you can write out the data definitions here. You kind of have to teach a trick here, right? Where it says the empty list. Sometimes you have these data things that only have one possible value. And for those, you just do an empty record type. So we kind of go define record, and we go, there's empty list, right? And there's make empty list, and we go, and then I explain, this is also the point where the naming convention breaks for the first time. We just call the predicate empty because we'll be typing it a lot. Okay. So, and then you can just go empty, make empty list. There you go, right? And then you can go, It doesn't really matter whether you do this bottom up or top down. You can do it either way. at some point, again, I'm doing an abbreviated version of this. You kind of go, well, okay, what are we gonna? What's the first element? Right? We need a first element here. So we're just going to start by saying, so we'll define something called a cons list. The constructor is called cons. For historic reasons, the predicate is cons p. I mean, by the way, right? So here's, I don't know if anyone knows scheme, right? In scheme, what's called cons is called a pair in scheme, right? Even though the constructor is called cons. And there's just these slight, right? The constructor is called cons, but the predicate is called pair, question mark. And students get really confused by that naming because they think a pair must be the same thing as a 2-element list, right? And so, somebody asked, what is one of the changes, right? And so we used to go with the scheme terminology, and we eventually changed it to this, and that's worked better. So we have cons, and then we go, well, we have first, and we also don't call it car and cdr, but that probably doesn't matter so much. So we're going to start with lists of numbers, and then rest. Well, for rest, we need a signature for lists as a whole, and you could do it, for example, like this. Well, these are only lists of numbers, so we're going to call that list of numbers. This is a signature. It's mixed together from empty list and cons list, and we put that here. So this is, and this is list of numbers, right? And so this is something that we basically just present to students, and I mean, we have more stuff coming out. I'll tell you more about other examples that we have, but this is just something that we work out in this exact form. And then you go kind of, well, here's a list with one element. This is really important. Yeah, it works. Really important. Did I mention that we have language levels? I really should have written beginner here. Because the difference between beginner and not beginners is that lists are built in. So just complain that I redefined something that already existed. So here it's really important to say, well, this is a 1-element list and consists of 5. So to really spell that out, right? Here's another element, here's this list. Oops. That people realize, oh, there's this nesting going on. This is a 2-element list. And so forth. Maybe with a 3-element list, you can do, I don't know, 2, 7, 5. You would start introducing this notion of sharing. So really important, again, if you're doing more complicated data analysis and data definitions, that you have examples and you have comments that explain the relationship between the information and the data that's involved. And then you go doing something simple. So here it's kind of, the examples are at first a little bit boring, right? So add the numbers in a list. I don't know, you could do something like list sum. And now realize that we can already do quite a lot with the design recipe and the template that students already know, right? So we already know that list of numbers, I'm sorry, you should have yelled at me and said, Mike, you forgot the signature, right? Right, so it goes like this, and maybe check expect list sum, list 3, and then it's 14, I think, should come out, right? And so, again, looking at the signature, we can see list of numbers. We can look up, seeing that's mixed data. This all gets excruciatingly bureaucratic, as you can imagine, right? And so you go, aha, because it's mixed data, there has to be a cond. Because there are 2 cases up there, you can see them at the top. There have to be 2 branches in that cond. And because we already know predicates for those 2 branches, we can write those out as well. So we can say, well, is the list empty or is the list a cons list? And in the case of the cons list, we can already write remember, in that case, we're dealing with compound data, so we can write out the calls to the selectors. So we write first list and we write rest list. So that would be the template according to what students know. And then we tell them a secret. If there's a self-reference in the data definition, and you're writing a function consuming that data, then where that self-reference is, you write a recursive call, so a call to the function that you're writing. So in this case, you write list sum of rest list. Now, what's important is you don't think about it. You write it before thinking. I mean, this goes with a lot of the aspects of the design recipe, is that you encourage people to write down something either without having to think a lot or without having to think at all. To really make sure, I mean, again, students, when they fail, they tend to give up with a blank piece of paper, or a blank screen in front of them. So anything that gets you to just type them more and more, get them to type more and more stuff is helpful here, right? And the thing with recursion is don't think about it, period, right? You write the recursive call, okay? And and you don't do this because it's the right thing to do or something like that. It's because I tell them to put the recursive call in. And once they've written it, they can kind of read out loud what they've written, okay? So they can say, well, can you read this? And they say, well, I can read out, this is the first element of the list. You can read that out loud, right? And you can see here, well, this is the sum of the rest of the list, right? And the rest of the list is all the list of all the elements except the first one. And then you ask, well, given those two things, right? Given the first element of the list and the sum of all the remaining elements of the list, can you figure out the sum of all the elements of the list, which is what we're trying to do here, right? And then they go, okay, I can do that from here. So we're not thinking about base case or any of that stuff, right? All that we're doing is we're taking the template, having students read that out loud. An alternative is so one way to do that would be, right, you go first element of the list. Maybe with another example, remaining sum of the remaining elements, rest elements of the list, right? An alternative is that you can also do, maybe on another example, is you take a concrete example. So for example, here's the test case of list 3, right? And you go, well, what is the first element of that list? Well, it is 2, right? And the sum of the rest of the list, well, that's going to be the sum of list 2, so it's the sum of 7 and 5, so that's going to be 12, right? And so that has to be 12. So knowing 2 and 12, and I want to get to 14, I don't know, how would I do that, right? And students can generally do that. So the strategy to deal with recursion is to get students to write programs without any larger understanding of the concept of recursion, right? That comes later. So you kind of get, you do it before you understand what you're doing. No I don't know, like nobody says fixed point or something like that in that platform class, I would hope, right? And then so people go, oh, we just add those two things, right? Then the more difficult bit is, when you're doing this, right, the more, I kind of on purpose didn't do the empty bit first, but depending on what kind of students you're dealing with, but I always have fun with the professional developers. I ask them, what should go here, right? And so you can have productive discussion where some people think, well, the empty list shouldn't have a sum. There's no numbers in it. I can't sum them up, right? Somebody will always say 0, right? And you will ask, why is it 0? And they will say, because it's like nothing or something. And then you might be able to write a function that instead of adding the elements of the list, just multiplies them. And then you go, what goes there? And they go 0 because we did the same thing there. And then you can have a little discussion about algebra if you like, right? Absolutely don't have to do that. So this is, but this is generally the approach that I've done many times that works well. So you then write a lot of functions over lists, right? That can segue into higher order programming. And then there's the recursion ideas right there. One thing that I'm currently experimenting with that also works well is instead of doing lists first, is doing something else that involves self-references. So so for that clear with the lists? So that works for recursion. So, but for the longest time, you don't deal with numbers, right? Later, you say, well, here's another secret, right? The numbers have this strict, there's 0 and there's a successor and so on. And then you can, because they've now written a lot of functions over lists, they realize that there's a correspondence between those things, and that's not so hard anymore. But really avoid doing functions, recursive functions over natural numbers for the longest time. So that would be, I think, the first hint. And that is easy. So compared to, I mentioned that at the beginning, the hardest part of the course, for me, in my experience, is always compound data. I can't tell you why. The way to do that is just to do it a lot, right? And to always, and really go, oh, your thing, how many components does it have? 3. Does your record definition also have 3? No, right? Right? I hold up fingers and so on, right? And to do that kind of thing a lot, right? And that tends to take the longest time. It doesn't matter whether it's beginning programmers or professionals. I cannot, even though you would think professional programmers do this every day, right? I have no explanation for that, right? But this recursion thing goes right by with no problems this way, right? What you definitely can also do, so here's just a fun, I think Matthias condensed this, right? He said, well, again, you don't know this, right? At the beginning of the 90s, the Navy, the US Navy conducted a comparative study of programming languages. The way they did it is they had an example problem, what's called a geometric region server. So they try to compute the area of influence of a little fleet that had like several ships in it and so on, right? And so the funny thing is that really my favorite part of the study is, so they did it with all kinds of programming languages, and then after the fact, they did it with Haskell. And Haskell did really well, but they did it with like one Haskell expert at the time and a beginner. And the beginner did it faster. And pretty short code, because the expert Haskell programmer was putting in the type classes and the whatnot, which are all kinds of pointless, used all the features in the type system and whatnot. So I think that sums up Haskell in many ways. Anyway, and I think Matthias condensed and says, well, here's a geometric shape is one of the following, right? You just put it down like this, and he said it's either a square, it's a circle, or it's an overlay of 2 geometric shapes, right? And then this is something that you can explain easily, because you say, well, what if 2, imagine this is like a fleet, right? There's like there's a boat that has a cannon that rotates, and I don't know what the square is, right? But you can have, what if 2 fleets like merge or something, right? They get together in whatever ocean, and of course their spheres, their areas of influence merge, right? Or union or combine or something like that, right? So you can explain that, and then usually this is like an example. This is the first exercise that we give, and that works kind of well. And then you take that from there. This is also a great example to discuss with other teachers, has been my experience, right? Also great question to ask during an application process, has been my experience, because you get really interesting answers. Because a lot of people trip, as you can imagine, a lot of people trip up here, right? Go, actually I have people come in, no, we gotta draw a line around the outline of whatever. Or some people think, don't take this too seriously, right? But I think you can see how that straightforwardly translates into, whatever, you're in Haskell some type, or what we just did is, 3 record types and some mixed data. And we have a couple other examples. So one that we have involves rivers. So right now, what I usually do is, as a first example, I do one of those. So I do a more applied example. So another example is a river, where a river usually flows together from 2 other rivers. So there's like a main stem and a tributary, things like that. And that also works okay. But it's my vague impression that the lists themselves do the job already. But I don't.
Can I be professional regarding this example, the geometric shape? This is where something that's quite similar to a problem when you try to teach the concept of an abstract syntax tree in Haskell. This idea that it's enough to have an overlay of 2 shapes.
Yeah.
You don't need a more general overlay. Don't you have to show examples how you do an overlay of 3 shapes using just?
Yes, you do that. I mean, as you can imagine, right? So a lot of times what people will do is they will do an overlay of a list of shapes or something like that, right? I mean, this is all things you can do that in Java as well. So this is the nice thing, is that it's a programming problem that Java folks can also relate to. So you can ask them, how would you do this, right? And I mean, again, right? I go and tell them, okay, this is fine. You did the list of things, right? But you didn't stick to the letter of what I wrote. Go back and do it the way that I wrote. And then we go, can we do more than 2 with this? And then they realize, oh yeah, we could just nest this, and then that breaks, right? It's not the other way. I find it fruitless trying to kind of explain the concept before having written the code. Right? That maybe I'm not explaining this right, but I just go, no, we're going to do 2. We'll see that later. Do 2. Not because we have an innate understanding of that is right or sufficient or something like that, just because I'm telling you to. And because you can explain, nowadays I mostly teach professional programmers, right? And they all, so there's a big movement called domain-driven design. I don't know, has anybody heard that? Right? So it's a huge movement, right? And domain-driven design has like 2 parts. It has something called tactical domain-driven design, strategic domain-driven design. And the tactical domain-driven design focuses on modeling, right? And so people really think that they're modeling something that concerns them, right? So, and this idea that, and the domain-driven design community, somewhat unproductively, has developed this insight over the years that you should model as close as possible to the formulation of your domain experts as possible. So when you're dealing with domain-driven design folks, I say, well, you're the domain-driven, the domain expert from the Navy said 2. Yeah, right? Right? So you're not supposed to abstract or doing something else, right? This community has learned to abhor abstraction, because in object-oriented folks don't know how to do abstraction successfully, right? It goes wrong a lot of the time. As are there's a couple of other things here. So there's a way to connect with these people, with beginning students. I don't know if that makes any sense. Okay, so far. Okay, so we got lists. As you can imagine, so the nice thing here, again, we did the teaching languages just so that, so this is, you notice, right, this is the point where we transition to the next higher level in the programming language levels. And the nice thing here is that we can write down the code here, right? And the built-in version is exactly the same, right? So we just comment this out and the code continues to work. What's also really nice, again, these are all things that we had to do. They didn't work naturally in the beginning. So in particular, one of the things that I think, well, here's a little didactic issue, right? Eventually you want to transition to polymorphic lists, right? Even with beginners, right? Because of course what you want to do is you want to stick the armadillos in the list and run over the entire code, right? Everybody can relate to that. So you can go at this point, right? So you can go, you could go and say, well, here's my highway, right? And it is cons, I think we had a Dillo one and a parrot one. In the actual class, we have more, but so we could do this, right? And a funny thing happens in that you get signature violations, right? Of course, because we set all the elements here are numbers. But highway, the program ran just fine, right? You have now a list of armadillos, so how can we reflect that fact? So here's something that I really like, and here's a thing that, well, it used to be worse. Let's put it like this. So somehow we have to generalize this, right? And I haven't gone over this because I think this is more familiar with you, is that very early on we established this concept of abstraction, that you have two similar pieces of code, and you very mechanically go and abstract over them by putting a lambda over them, by copying it one more time, putting a lambda over it, and so on. We can do that. So here we go, well, okay, we got to start somewhere. So what we do is we take the concrete thing out that might be different. So this might be number or it might be animal, and we replace it by a more general abstract name. Okay, so you can go here and you can write, well, it's not, obviously it's not supposed to be number, we're just going to call that element, right? Students also know at this point that names need to be bound somewhere, right? And that names get bound by define or lambda in these languages. You're writing lambda out and so on. That's, of course, also a didactic device. And the thing is, define record, right? It's this complex form that generates a lot of definitions for you. And there is a lambda in there, but you're not seeing it. It's generated by the form. But you can get it to stick in a lambda by saying, well, I do this, cons list of element. And that always feels like a little bit of magic. Maybe you know a way to put a lambda here. I wish I could put a lambda here. But once you get over this little bit of magic, you can then go over the rest and go, oh, well, that means I need to go down here, right? I have cons list down here, so that no longer exists. I need to write cons list off. And of course, then I need to put the name, but the name is abstract. So I'm supposed to, so this numbers needs to go. And given that we have this element, we need to have a lambda somewhere. So we put a lambda here. And so you can do this step by step, and then you kind of run it, and it says, oh, there's still a list of numbers here. So you go, so you also write list of element here, and I think that's almost it, because then you go, oh, but then there is still, well, we use that list of numbers somewhere, but then you can go, well, list of numbers is the same thing as is a signature. That's just list of number. And so we carefully, so that's kind of evolved over the years to kind of go down well, or as well as I could make it. And it works. I'm still not entirely happy with that cons list off, because you got to tell, well, through the fact that we're writing an additional pair of parentheses, internally it's sticking in a lambda, right? But I can assure you the versions that we had before that were much more awkward. So that's the best I could do at this point. So here would be something to think about that you could do. And this you can now just comment out, wholesale, switch to the next higher programming language level, and then that's done. But at this point, once we get through it, people can program with lists. Somewhat to my chagrin, is we sometimes, I mean, of course, you can imagine that there is a chapter on higher order programming, and somewhat to my chagrin, we introduce folds, and then they go crazy, right? And they go back. I can't explain it in class. They go, oh, we gotta go back and do everything that we ever did with folds. I think sure, I'm just wrote a paper where that's fold is not the best sort of didactic device, and I completely agree with them. But the students kind of go, oh, we gotta do that. So yeah. So that's how we gotta get over recursion. Any questions on that recursion bit? With maybe another reference point out for the beginning students, even though I'd like to try that out with beginning students once, but with the professional students, one thing that's worked exceptionally well as an example. So this is mainly, I mean, as you noticed, right? This is an example. So the lists kind of fall down from the sky, right? We tell them, it just turns out that this particular way of doing it is very convenient. You could do it some other ways. You usually have exercises, and you could also have zero element list, one element list, and kind of append as the constructor or construct them from the back. All of that stuff works. And then there's, this thing, well here, which is kind of which has inherent self-references, or if you go to the river, tributaries and stems, there's also inherent self-referencing there. But of course, the really powerful models are created from you go from it does not have self-reference to it has self-references, right? I don't know if you've seen that. So one example, one thing that I found really well to explain the methodology behind that is an old paper on financial contracts by Simon and a French trader called Jean-Marc Hébert. And so we do, and so that's something that works exceptionally well with the professionals and like to try it out with beginners, because you actually go and make up self-references that are not inherent in the way that a domain expert would talk about these things. So that's always a lot of fun. Recursion. So far, so good. Okay, so let me summarize. You just don't do natural numbers in the beginning. That's the main thing, right? Put it in the data, and then you can explain the relationship between the data and the function that you're running.
Do you have some objection to introducing sort of piano natural numbers as?
Not at all. That's what we do, but you do it later. The important thing is that you do it later, right? You do it later, right? Once you've done this, right, and really done this a lot, right, that people are really, really not scared at all. I mean, some of it are, you might remember, right, your traditional computer science class, right, has some element of recursion, but there's always this specter. It's hard, right? Everyone knows it's hard. The teachers know it's hard, and so on, right? And some of that sometimes rubs off on the students, so you really need to make sure that people are not concerned about this. They realize it's a completely natural thing, and then you go, oh, by the way, here's how we can talk about natural numbers. And then it's no problem as the second example, or the third or something, right? Just not the first. As with a lot of stuff, right? Your favorite stuff, you can do it. It just doesn't have to be first, right? So this is of course all structural recursion, right? And so that's easy to do, right? But one thing I think is that we should, that is important to teach is, well, we should also teach about iteration, right? And the way to do that, of course, in these languages is to use tail recursion, but you don't really want to talk, you really want to talk about the iterative process that's there, right? And and there you can't, you can have a variation of the design recipe and the template, right? But it's no longer as deterministic as the one that involves structural recursion, right? Because people have to think about intermediate results, and there's no guideline for that, as far as I know. You can help them a little bit, but essentially you have to, you have to tell people, think of an intermediate result, think of a loop invariant, and then try to preserve that. Right? That's just hard. I think mostly students, of course, the professionals, right, come in and think, why can't we just write a while loop or a for loop, right? And because they've gotten it into their head that writing a while loop or a for loop is easy, but if you really ask them, if you just ask them, is it really easy, right? And they think about the last couple of loops that they've written, unless it's just a loop that goes over an array or something like that, right? They realize, oh no, I've made quite a few mistakes writing while loops or for loops, right? And there's empirical studies that show that it's just hard. So that would be, we push it to a certain point, right? We go, okay, you think about the intermediate results that you want. You can think about kind of the progress that you've made as related to the progress that you still have to make. You can kind of give them a template for the loop invariant and so on, so you can help them along, but it still seems not quite satisfactory. So that there is some direction for further work. Definitely. Yeah.
how do you deal with some students who have already some experience in interactive programming before the class?
Yeah.
And some of them naturally come up with solutions that involve writing later, and the natural way of thinking functionally is completely unnatural to them.
Yeah, but they don't know how to write it down in these languages, right? I mean, here's, of course, I mean, this, I've forgotten about this, right? Because, I mean, so I mean, one of the reasons, right, is why you have these language levels, right? One of the most important things is to leave out setbang, right? To leave out assignments. Maybe that's the single most important feature of teaching languages, even though full scheme or full Racket has it. It has assignments, right? Because students would in the old dark ages, right? They would go look up in the manual, how do I change the value of a variable, and then they would do what you say.
Okay, but even without.
Even without, they write recursive iterative functions?
Some
Seriously?
of them, yes.
I have never seen that.
Okay.
Honestly, never. Not a single time I've seen that. Interesting. Okay.
It's clearly not the majority of this.
Yeah. I don't know. I have no idea.
I have seen it.
I mean,
on
is
both
that-
sides.
the first question I think is that
some
sort of-
labor instead of a simple synthesis of a result.
I mean, so one thing to try out, I think, would be to try this.
Oh yeah, then
Right.
we're completely lost, of course.
Right? And say, well, go do this, right? Which has, if you're not seeing it right, it has two self-references, so at least it's not obvious how to do it iteratively, where that would be considerably harder, or to do the example of the rivers, for example. So in the textbook that we have currently, the first example for self-references is one with rivers, where you have a tributary and a main stem, and also their iteration would not work. So maybe that would break through that. Of course, again, with the professionals, you're going to attach an entire discussion about the stack in the JVM or whatever to that. So that's you can attach a lot of kind of understanding on that subject. Yeah, so iteration would be interesting because right now the facts of the matter are that a lot of languages force you essentially to write iterative functions for a lot of things, and so we ought to be able to teach them. I'd like to be able to teach them better. So grateful for input on that. So, anything else that you're interested in?
I can understand your point, but I think the difficulty is really that iterations are all very different. There's a different argument why a certain loop invariant holds, and
Yes.
so because there is no structure, there is no general method
Yeah.
to teach it.
Yeah.
To students, you have to do it in a case by case way.
Yeah.
Whereas a structural recursion follows the data.
Yeah, absolutely. Yeah, okay. So, I mean, I'm just maybe there isn't a better way to do it, right? But it would surely, sure, it would be nice if we had one, right? That would get rid of, or that would maybe not eliminate, but yeah, my hope is that it would eliminate a large number of bugs that people are introducing into software because we don't know how to do this. We don't know how to write loops. That'd be really nice. Okay, recursion. Maybe one other place where the self-references occur is, let me do it slightly. So let me point out that the way that we're currently advertising, and we're just transitioning, is that you would choose the programming language using a menu item here. So you could do that too, instead of writing that #lang line. But right now that's still there. And what you can do is there is what's called a teach pack, which is just a library. And there's a really nice library called the image library, which I take 0 credit for. So the PLT folks have done that. And that's something that we actually do at the very beginning, usually to show I mean, students understand that you can calculate with numbers, right? But calculate with other things as well. So there is a little library which has functions like circle, right? And so you can do something like this, right? You can make, whoops, sorry, more time. So now it should work. There it is. So you can call a function like circle, and it will give you a circle object that the REPL then prints as its picture, right? And what you can do is you can combine them in various ways. So you could go, maybe if this is circle 1, or here's a star 1, solid green or something like that. So, so this is really something nice, and everybody gets pretty quickly that there's a difference between having like a canvas and drawing on it than having a circle object. So that doesn't require much explanation. And then you can go and go something like, for example, above circle 1 star 1, or overlay star 1 circle 1. Right, and so you get combinators. So you can, I mean, people understand. I think they kind of have an intuitive understanding at the beginning, but you can, when it comes to self-references, you can go back to this and say, oh, well, okay, so something like this must have been going on internally, right? Maybe I should demo one more thing before you think, oh, I could do all this in Haskell. But what's really nice is I usually do this thing where you kind of go have this pattern where you go, okay, I want, so there's also beside. So I have circle 1 and star 1, and I do this. I'm putting tiles in my bathroom, right? So like this, right? And so you get this kind of square pattern with alternating tiles. And then you get this idea that, somebody comes visit your bathroom and says, oh, that's fine, but instead of the star, can I have like a square, right? And then you go, oh yeah, sure. So I'll make a square that's like solid gold. I'm sure that's gonna look pretty. And then you go, okay, so here's your bathroom, which goes like square 1 and circle 1 and circle 1 and square 1. So now we have this. Okay, looks really pretty. And then we can naturally abstract over those two things, right? And so then you go, okay, all your friends come and want the same pattern with different tiles. So you open like a tile layer business or something where you just put that in your catalog. So you copy it one more time. You stick in image 1, image 2, and so you choose abstract names, and then you put a lambda into abstract all of these things. By the way, it used to be, I think there was even a paper at the educational workshop like a zillion years ago where we thought the naming of things would be important, right? We shouldn't say monad or something like that, or lambda. That would just scare people off. That is complete, utter nonsense. It's not the names, right? Names are cool, especially names like lambda. My very consistent experience, right? You could call this fun or something. You could, but there's no. I could I could turn this into a function, and let me comment this stuff out. And of course, you can then call it and go the way around, right? So square 1 and star 1. So you can just call it, okay, gives you a nice result. And there's a nice little button here that my friend John Clements wrote many years ago called the stepper. And the stepper visualizes program evaluation, right? And it also works with the pictures. So you can say, oh, there's a difference between the expression up there and the actual circle that it represents, right? And you can go, okay, so there's the star, there's a square, and then you can say really nicely, oh, the names get replaced by their values, right? This is also great to see, again, for the professional programmers, right, who go like, why do I not have that in my Java debugger? And then you can go, oh, that's because you can't just replace a value, a variable by its value, and then you can go on from there. So literally, it will go saturate the application, substitute the pictures, and do this. And that is also really nice didactically, the stepper. And especially in connection with things like the pictures and so on. Okay. Anything else? So again, if you want to play devil's advocate and want to ask, why, what is an issue here, then please do. Or you want to go, or any other question?
A colleague of mine who was here but couldn't make it to the session wanted to know how much you cover. And do you sometimes cover the whole course? And how much material can you cover? He's worried because he also wants to teach them some algorithms. And he wonders how much this idea of recipes can transfer. I know I'm straying a little off to the side now.
So no, not at all. I mean, so at the university that I taught, this would be a class that would have 4 hours a week of lecture, right? And it would be a semester. Semester, I think, is 12 weeks, 14 weeks, something like that, right? As I said, about halfway through, we get to doing, so these pictures, they can also be animated. That's the part I forgot to mention, right? There's you saw another teach pack here called the Universe teach pack, which can even do that in a distributed fashion, but it just gives you a couple of functions where you just write, where you create a model, you write a function, and you write how that function, you write a bunch of functions that tell you how that model reacts to user input, and then how to turn that model into a picture. So it's a really nice modular way of writing video games as well. And then you can do animations, and from then you can do video games. That is halfway through that semester. So if you're satisfied with that, you could do a bunch of algorithms, if that's what you like after that, right? If I do a professional class, right, in 2 days, we get up to, we don't do video games, we're professionals. We don't do video games, but in those 2 days, we get up usually just about to, so we do a lot of higher order functions and list programming, and we cover usually iteration, and usually because that's interesting to the professionals, it's the stuff with the tail recursion, right? So that happens after 2 days. I don't know how that relates to your coworker stuff. What we do in the university class is, maybe for historical reasons, but people said really wanted to do that. We also do a section on lambda calculus. Here's also maybe an interesting insight we try to, for the longest time, I mean, List is this really cool idea of the meta-circular interpreter, right? Don't do that with your students. Right? Really cool idea. Also, and another thing that you might have noticed, if you know Scheme, maybe you didn't see this, but, oops. Another answer to the question is, how did the programming language change, right? If you print that list, it prints this nested structure, right? Even if you crank it up a level, that is, if you comment out all this stuff and switch to the next highest level, so I remove the beginner, work quickly. It prints it like this, right? And if you're familiar with classic Lisp, that gets printed with parens things, parens closed. Which, of course, you can provide a sensible explanation, really cool homo iconicity, whatever, things like that. Don't do that with your students. So we found it, students were, and of course this has downsides, right? You can't copy and paste this thing back into your program, which you could if we used list style quotes, right? But it's been very helpful for our students to realize that these things are distinct, right? And then later, once all that is covered, you can go, oh, there's a different way of printing it that will make the printout look like a program, right? But by now we know what the data structures behind it is. So we always wanted to cover a little bit of, semantics or something semantics by doing meta-circular interpreter. Don't do that with your students. To my surprise, so generally we were surprised that students were able to really deal well with the lambda calculus and beta reduction and things like that, which you would think, right? No, you don't. Well, you don't in this room, but normally, going into this, we thought students would hate it. They don't, they loved it for some reason that we can't explain. And the semantics part we ended up doing the SECD machine as an experiment, which also worked fine, right? Much to, again, so we zapped the meta-circular interpreter chapter, put in the SECD machine, and people are able to deal with that just fine at the end. But of course, if you do a regular course, this is not, this was just because we thought it was cool. You don't have to do that. And so again, this is where you might stick in algorithms. As a professional programmer, I have to tell you though that I think that algorithms are completely uninteresting and unimportant. They're not completely unimportant, but there's so many more important things that do not get the same kind of priority in university classes. But in day-to-day programming, professional development, somebody else has done the algorithms, right? And the problem, and there are algorithms-based intro courses, right? And straight from hell, right? So my former boss asked Tony Hoare, right? How did you come up with quicksort, right? And Tony Hoare said, well, the first idea was bubble sort. That obviously sucked, and that was my second idea. That was the extent of his explanation, right? And you can imagine, later in the class doing some kind of divide and conquer, but most algorithms a lot of the kind of cool algorithms can't be explained in a systematic way. And that is just super discouraging for students, right? Oh, here's something you could never have come up with yourself. Isn't that, no, don't do that, please. So the things I've seen over the years at didactic conferences, I think the worst was where they had an actual didactics professor who said, well, we realize our intro course based on algorithms is not working. And it's a mystery, right? So they said, well, and so we realized over the years, we've realized there's students who dig it and there's students who don't. So what we're going to do is we're going to stick a camera over the shoulders of a student who digs it, right? And just show it to the other students, right? And then you probably presented that video and the video was going like, and then there was some problem. I don't recall what the problem was, but literally the first sentence out of the digger's mouth was, oh, this is obviously a recurrence equation. And don't, yeah. So please don't do that. Find a way to get everybody on board. That would really be cool, I think, and not just, just do that. Any other things we might cover? So we don't have to stick around. Just finish whenever we want. All right.
Do you do any sort of generative recursion or infinite structures?
That's a good question. So Matthias has a chapter on that, right? And that goes in the direction of algorithms. And we used to have one, but I just thought the other stuff was more important. So I'm thinking, it's kind of, there's a queue of things I'd still like to write, and this is one of them, but I think it's not very important. I think this is, in the sense of that you're probably not going to need that much in practice, right? If you do algorithms, you go into research for algorithms, then it might be more important, but generally folks do fine without it. So generative recursion is stuff like quicksort or something like that, right? Where you divide where you take a problem, essentially divide and conquer, divide it into smaller problems, and then you
That
compose
was
the
what I was
solution.
thinking, maybe I'm using the wrong term. I was thinking like generating a stream of data or processing a stream of data, things like that, where you're doing not a finite data structure, but an infinite data structure.
Okay, then that's something else. So generative recursion is a specific term in how to design programs for what I just explained, right? So it's not structural recursion, but it's instead.
Okay.
Jeremy Gibbons has a nice approach to this where he really explains it in terms of generation. Maybe the term makes more sense, but this approach is not fully developed yet. So infinite data structures. We do that usually in the exercises where people don't seem to have so where we explicitly have people program with thunks, right? So homemade call by value, that call my name. That seems to work okay, but not really as a super important part of the thing. It plays a more prominent role in the functional architecture class that we teach, if I may say so, but it doesn't. I don't think there's any particular difficulty there. Once you know that you can have laziness by just wrapping a func around something.
In the previous session, we were talking about the really excited students and the really exciting teachers, and I thought that was really cool. Could you elaborate a little bit more on the harm that you see being done when the teacher presents computer science, because it's a really exciting thing. I definitely experienced that at university. The teachers were the ones that did that.
What was your question?
Oh, I just wanted to ask, what is to ask you to elaborate on the harm that you see that doing, or
I'm not sure it does active harm. We just didn't find any value in trying to provide that positive motivation. But to expand a little bit on it, so I mentioned that we try to do this positive motivation thing up to a point, right? In a lot of ways, right? Where we try to sort of encourage people to do their own thinking and I would explain to them, right, all of this, function, but this is why this is the greatest thing ever and whatnot, right? And people whined about that, that stuff anyway in the course evaluations. And so, we decided that for 1 year, we were going to do everything the other way around, right? So just to give you an idea is that the first lecture I would previously have spent on trying to put a positive spin on what we were doing. And that year, I cut off my hair, I put on a suit, I went in class, and I said, well, folks, and I put on some study that the ACM had published that said, well, if you learn standardized tasks, your job is going to be outsourced to India. Okay? So therefore, we're not going to teach you what everybody else is learning or whatever, right? Then we would give them a math test. So zero positive motivation, and we would just say, we're just going to cover as much material as we, so that you can have a job when you graduate, right? Otherwise, you're not going to have a job, right? So implication. So we were really, and whenever somebody complained, so much as hinted at complaining, I would just go, "Who is the professional here?" Right? And that took care of and so two things happened, right? The complaints stopped. I'm not saying you should do that, right? Success of Thorsten Groß is really nice, and he seems to be succeeding as well. But two things happened. There were a lot of other things that went along with that, but generally performance went significantly up with that. I think generally because our students, right, the students in Germany who graduate from high school just don't know how to learn on their own, literally. It's not their fault. It's just because school did. I could go on and on about this, but school doesn't teach them how to do that. But the class evaluation was as positive as the year before. It did make, to like 2 digits after the decimal point. How do you explain that, right? So the class was as popular as before, despite the fact that I didn't even smile, right? So
when you say performance went up, how do you measure performance?
Wrote a paper on it, looking at the final exams. So we might try to make the final exams correspond between successive years and then compare them. I mean, statistical significance is probably limited, but I mean, you learn a few things from that. But we've actually published, so if you go to my own page, then you'll find publication on that. So I mean, generally, not just with professionals, right? I have stopped trying to tell people how great functional programming is. They'll figure that out themselves. Really, seriously, don't. It's neither necessary nor does it get you anywhere. Right? That's been my very consistent experience. And I've done this more years than all of you. Right? So, all right. Good. There's also-
Unrelated question. I see the memory consumption keeps getting up.
It stops at some point. But what it does is, I mean, it probably is excessive, but there's an excessively excessive amount of annotation that goes on behind the scenes, which will also provide things like coverage annotations, which we haven't looked at, and things like that. And just generally, Dr. Racket is just as a baseline, uses a lot of memory, but it'll stop at some point. You're right. Yeah.
You said you use the word lambda
Yeah.
when you teach. So do you introduce lambda calculus to professionals during the
No.
3 days course?
No.
How do you explain why you use lambda? Is it just like for history reasons?
No, they know this. The things it's called lambda in Java. No.
I mean, I bet there are different concepts.
No, people, they know this already. I don't have to explain it to them. They're called lambda expressions. They're literally called lambda expressions in Java or C#.
Don't they ask why?
Well, if I ask them, then I tell them, well, there's this typesetters accident that happened to Alonzo Church's papers in the 30s.
Okay.
That takes about 5 minutes, and then you can move on, right? And then,
Yeah,
So-
this is just the thing about scary terminology. Monads are the same.
well, it's the same, right? Again, I think people mostly would say the name is the thing that scares people away. That this is an argument. If you look, it's always made on behalf of other people, right? I mean, there's plenty of scary terminology in Java as well, right? And it doesn't seem to scare people off. People appreciate the fact that a specific thing has a name, right? It doesn't matter what that name is, right? I mean, the thing where you can, I think, where there's more justification is complaining is when you say semigroup, right? So why do you go from semigroup to monoid? And group is much later. There's somebody obviously screwed up, but monad? I mean, the fact that it's a name that doesn't relate to any metaphor is a feature, not a bug. Yeah, right? No, seriously, and people understand this, right? People get this, that things have names, right? And that names sometimes come out of thin air, right? They're familiar, this is no different in the right, there's things called whatever, the disruptor or whatever, it's a specific thing, right? The strategy pattern, right? All these things. This is not an issue at all, ever. Or at least I've not experienced it, right? In fact, I've given a number of monad talks that had monad in the title at Java developers conferences, and the room was always packed, right? Going in, right? So how do you explain that? I think you explain it, right? Monad, oh cool. Is what people go, right? Doesn't seem to scare them off. Yeah. So not all my talks are packed, right? But the monad ones, right? Always packed. Oh.
So the book you talked about at the very beginning from Emerson Sussman.
Yeah.
So now that you have acquired all this great experience about what works and what does not in teaching, do you think that any parts of this book could be used in a successful way?
In an intro course? No.
Yeah.
No, this is a great book, but read it after the intro course.
Nothing.
But in the intro course, zero. Really zero. There's nothing in there. I'm sad to say, right? But really, I mean, right? And the initial mistake is already using MIT scheme, right? Of course, they would use MIT scheme, right? It's from MIT. right? But no, unfortunately, great stuff. But and we don't have to. It's a great book. We can do that second or third or something like that, right? It doesn't diminish the greatness of the book that it doesn't serve as a good introductory book.
I mean, this is also an historical transition, because in the 80s, most people going into computer science had started using home computers, and they knew how to program something before they went to university. I mean, I learned BASIC and Z80 assembly, and I went to university. I already knew some programming. So the point of the MIT course was to teach something to people who already know how to program, already have an idea for an operational semantics of a machine, but now they want to learn abstraction.
Yeah, but even there, success was limited. The success was limited. So, and it really, I mean, if you go, I could show. I mean, the things when I started in the '90s, right? I started before I was aware of Matthias's efforts, right? Really, ours was pretty much a German version of structured interpretation of computer programs, and over the years, chapter by chapter, it got rewritten because it didn't work. So, but I really mean none of it, because we did all of it, and then bit by bit, we took it all out, right? Because we were able to do better. All right, should we close? Thank you very much for all that discussion. This is always interesting. I mean, I'm doing this for the 5th or 6th time. It's always completely different every year. So I appreciate your input, and I hope you got something out of it. If you have any issues or questions or input later, or more, try stuff out, let me know. I'd be thrilled to get to hear from you. And have a great ICFP.
Thank you.
Thank you.